Hi, welcome to the Signal Path short episode. I was going to take a look at this Anritsu MN9610B. This is a programmable optical attenuator and it doesn't work, it's broken, it has some problem most likely in the free space optics section that we're going to take a look at. I'm not really interested in fixing it. I don't think it's really worth a lot of money and it's not worth the amount of time and the effort, and fixing it would be quite difficult and you need to calibrate it. Anyway, it's not worth it. I actually have a working version of this in the lab, so if I really wanted to, technically speaking, I could have done that, and it's all the way at the end of the lab. You can see it's got those green legs in it. In that end of the section of the lab is where I kept all the optical equipment. So anyway, I thought it would be interesting to take it apart and take some parts from it, maybe spare parts for the working unit that I have, and also take a look at the optical section where attenuation happens. So it's going to be a quick video taking a quick look and taking it apart. Should be fun nonetheless. So let's go. Alright, and here's a look inside the unit. Very nice and clean construction from Anritsu. Now, as I was mentioning, this is a free space optic attenuator, and based on the fact that all the attenuation seems to be handled in this box and there's nothing going in and out of this box except the input and output fiber, this must be a purely passive attenuator. So there are no semiconductors, no liquid crystals, there's nothing in there other than some mechanical mean of creating attenuation, which I'm not sure what that is actually, and I'd like to open it and find out. Now, creating optical attenuation itself is not difficult, but creating controlled optical attenuation, repeatable, is very tough. And then making it flat across the frequency in terms of attenuation across wavelength is harder yet again. And the way this one seems to be working, it's got two stepper motors or two DC motors that have precise position control, and you can see them spinning here. And there's some feedback mechanism reading perhaps the position of these motors with respect to whatever's on the inside, and then there's some motors underneath this board which spin these. And since there doesn't seem to be any active feedback within here, the position of the motors must be pre-programmed after calibration in some memory, and it just recalls that and then spins the motor to where it's supposed to be and then stops. In fact, if I've plugged it in, if I turn it on, you can see that the motors do spin. Now, if I change the attenuation, which like that for example, see, now I'm at 0 attenuation. Now at 0 dB, I would expect it to spin for some time and then stop. And it doesn't seem to do that, it just keeps spinning forever. Now if I go to 10 dB attenuation, still spinning at 20. Okay, there you go. You see at 20, it's unstable. It doesn't stay still, even though the other one spins and then stays still. So you can clearly see that there's something wrong. That tells me that the feedback mechanism that controls the motor within this section is broken. It seems to be purely an electronic problem. Nonetheless, not worth fixing. I just want to salvage some parts from it, and the displays and stuff, and maybe some of the knobs, and definitely want to see what's in here. But one of the other reasons I really want to see what's in here is because of this label. It says, "Do not remove this cover. Removal will cause permanent damage to the instrument." Why? Why would it cause permanent damage? I really must know. I really want to figure out what's going on there. And I've actually connected it to my variable isolation transformer just to see the power, and it's burning 18 watts when it's on. It's pretty interesting. Let me see what happens if I try to stop this. Oh, I can do it. There you go. It just stabilized. And if I go back, yeah, it's still unstable. You can see it doesn't stop. So something's wrong there. And this will cause the attenuation to continue to do this, so making this completely useless for any application other than very maybe in some of the attenuations it will stop. Yeah, for example, when I go to 30 dB, it stops. So it's not working at all the attenuation levels. Anyway, so let's go ahead and turn it off and unplug it and start disassembling and see what happens. So first, the logic board, nothing unusual. We've got two erasable, UV erasable memories here, and these are likely storing calibration coefficients and so on, and the firmware. And then there is here, this is a Hitachi SRAM, and this is an NEC 4 MHz 8-bit microprocessor, and this TI part may be related to the GPIV, I'm not quite sure. And then this is a 4 MHz crystal, some backup battery for keeping something active in the memory. I'm not sure. I'm not even sure why they need this. Oh, okay, I think I know. It's because this unit remembers what the last attenuation setting was, and that's probably what this is for. And then you can see a whole bunch of other logic. Nothing unusual. We'll save that as it is. But here we can begin to see some of the mechanical stuff. We got two motors here, and interestingly enough, these motors seem to have their own either step counter or position counter built into them. This is probably for power. And then there's this interface between the motor and some other type of detector or step counter, or some kind of an encoder there, and they're collecting all of this information and feeding it into another PCB, which is at the bottom of this instrument. And there's one of the fibers. This fiber is the fiber coming from, if I'm not mistaken, the output on that side. So you can see it's pretty straightforward construction. So we're going to save all of this, and you've seen me use one of these parts before. This allows two rotating parts to be connected to each other, and then these little slits that you see in the body allows this part to flex in this direction. So if there's a misalignment between the core of this motor and whatever it's connected to, that would mean that if there's a wobbling, this would absorb that misalignment and it wouldn't twist and bend the entire chassis and causing this whole piece to be shifting, because you will need very, very little misalignment to totally throw off the attenuation, because we're talking about nanometers here. So interesting that they're using these parts. So these are all very valuable and worth saving. The motors must be quite good as well. Definitely useful for something else. Now if I flip this, on this side we have all of the analog circuitry, and you can see all the drivers for the motors, the voltage regulators, quite a few fuses. There are some filters over there. And this, the whole section here, there's a lot of test points allowing you to check the different feedback voltages and stuff going around. So we'll save this board as it is also. I don't think it's really worthwhile going through it. A lot of op amps clearly for the feedback, and it looks like a lot of this feedback mechanism is done in an analog domain, and then the digital values come in and set that somehow. Perhaps I wonder if it's PWM or there's some DAC in there. I have to look at all the part numbers. These two might be DACs. Yeah, these are 87538. I don't know. We have to check to see if these are DACs. But either way, you can kind of get a rough idea of what the architecture of this is. Yeah, it's pretty straightforward otherwise. So let's go ahead and disassemble this too, take this whole thing out, and then we get to the nice mechanical parts. Let me point out a couple of other things. By the way, these are DACs, which means that the system is now very clear what it does. You know, they load the data into the DAC. The DAC creates a reference voltage. The reference voltage is fed into a simple feedback network, which then sets the position of the motor. It's really easy to follow. And it's kind of cool to see how much detail the Japanese go in designing some of these. The connector for one of the motors to the board is a different color than the other one, so that they know which one to plug to where. The Japanese are very meticulous, just like the Germans, in the way they design this. I always enjoy looking at their work. And here's the power supply section. Very nice low profile power supply as a single module. Pretty happy to take that and use it in the future. Also the power plug, quite nice with built-in fuses and everything. Like these things, you know, if you were to buy these, it's quite expensive as they are. A nice filter there on the AC line. And look, what they've done is that they've wrapped the AC lines going into the filter with further shielding that's grounded to really contain any field coming from here. Because remember, before the filter, this is where all the noise is. Afterwards, the noise is, most of it is gone. And they have a nice screw terminal. Very modular design, as with most instruments are, because you can afford to do that. You're not really building them down to cost. So pretty interesting to see. Let's take all this stuff out as well. And here's the front end display, and look at how neat this is. This is pretty cool. So this is the main rotation for adjusting the attenuation. Now once you put this in, you can rotate this, and obviously has an optical decoder, because you can see the slits here, and there must be some diodes and infrared diodes in there for detecting them every time a rotation is made or a click is made. And interesting enough, it also has 4 buttons on it, and these buttons have a spring on top, and they go all the way inside this module and then make some contact so that you can distinguish between first, second, third, and fourth. So it's a really neat little, I've never seen one of these before anywhere else except on this Anritsu part, and I really like it. I'm sure we can find a cool use for it in a different project. The rest of it is really nothing fancy. You got some green, the color of Anritsu, 7-segment displays. There's a LED there for lighting up some warning in the front, and the rest of them are just push buttons that have LEDs embedded in them. Pretty nice, and then there's some controller for the 7 segments, it looks like. But oops, there it goes. Other than that, neat and simple. And here's our power supply. It's actually quite a good power supply. This is a Lambda. This is made in Malaysia. You can see the specification here on this component. This is ZT35FF. It's got a 5-volt output at 3 amp, plus 15 at 1 amp, and minus 15 at 0.3 amp. So it's a nice, neat little power supply, very low profile. The back here is not the cleanest thing in the world, but look at this huge separation they have here between the live section and the output, which is quite nice. It's nice to see. And the traces are this very old style, and even they've got some places where they have doubled down on the solder in order to increase the current handling capability. This is obviously done on purpose. It's clearly wave soldered, Not very clean soldering. I'm not quite happy about that. But nonetheless, a simple little power supply. I know I've kept you guys waiting. Now we're gonna finally get to take a look at that. Alright, I've taken all the screws off except the last one that has the glue on it. We can now break the seal. Let's see now. Oh, interesting. The glue came with it. There we go. And let's see. Now I guess that there must be some kind of a grading mirror or a grading transparent section or something in there. Oh, disconnected anything to it? No, nothing's connected to it. Ah, take a look at that. Yeah, oh, that is cool. That's exactly what I was just saying. Very interesting. So these are discs, and you cannot see from your angle, but these discs have a coating on them. And that coating is gradually decreasing across the radius of this disc. So remember, the light is coming in this way and then goes out that way. So this should have collimators on it. Otherwise, how are they doing that? And most likely does. I can't see. Yeah, it does have collimators on it. So you can see, oh, and they're of course with different amount of attenuation. So this is the most significant attenuation portion. It's the least significant. Very, very cool. I'm going to take that apart further to show you. This is a very cool design actually, and very simple. And the inside of this is purposely, looks like it's kept rough so that internal reflections don't build up and it's fully scattered. At least this is my guess. This is why probably they would have done this as opposed to making it, you know, nice and shiny like the rest of it. But very, very cool. This is a precision instrument. Now, it's very obvious to me that this has no feedback. So they calibrate it and that's it. And there's really not much else you can do once you calibrate it. It's a done deal. And let me see if I can put it in an angle so you can see what I'm talking about. Let me see if I can get that for you. Yeah, there you go. So then you can see the mirror. Now if I turn the mirror, you can see, do you see? This is the part that is fully transparent and it slowly gets darker and darker and darker. And then after this point, there's nothing. Now if you look at this one, you can see the boundary here very clearly. If I go there, it gets darker and darker, and the light goes through this one first and this one first, and there's an accumulated attenuation across both of them in order to provide the final attenuation. So now you know exactly how it works. And there's a light enters from there somewhere at the bottom and then goes through to the other side, because as you can see, this is the fiber coming out there. This must be some kind of a collimator there, and the other one also. So the focal length of those collimators must be lined up perfectly. Otherwise, you're going to have unnecessary extra insertion loss into this attenuator, which you wouldn't want. Very, very cool. Now, even though these are designed for infrared frequencies, they also exhibit a similar behavior in the visible range. That's why we can see the attenuation change with the location on there. So I'm pretty happy with it. Looks pretty awesome. I wish I could plug it in so we can see them spin, but I guess all you would see is just basically what I'm doing with my hand. These guys will just spin. That's really all you would see, and this one wasn't stopping. So it's just doing this, and you can imagine if I do this all the time with it as it was unstable, you will get a horrible performance because this attenuation would constantly be increasing and decreasing. Now, I think this can come out as a whole module, so we can take it out as a whole module and maybe just keep it the way it is and see if we can spin the motors ourselves. But I'm curious to see what this feedback is. So maybe as a final thing, we can just quickly measure that and understand what it is that we're looking at there. And I'm actually looking at it now. It's nothing more than just a potentiometer. Yeah, I can see it. It's a potentiometer. But nonetheless, let's do a measurement on it. So there's a couple of other interesting things to note about this. Well, first of all, the incident of the light going into the unit from one of the collimators that I've taken off is not straight. And that's to be expected. This is something that we've seen before. It's at an angle so that when the light goes in and hits one of those discs, it doesn't reflect back out precisely back into the fiber and reflect back onto the source. So they make this at an angle such that the reflections are contained within the unit. And that kind of make consistent with the fact that the inside of the unit surface is very rough. Now, other thing that's interesting to note is that initially when I took this screw out, I wasn't paying enough attention and I thought that this might be holding this down, but in reality this is actually not connected to anything. But it turns out that by examining the fact that they have an O-ring style block here and looking at the inside of this whole thing is hermetically sealed. So what they do is that they probably purge the air inside with something that's, you know, not very reactive, maybe a noble gas, maybe argon, or something that's non-reactive at all, because they don't want the surface of the coating on these mirrors to be compromised by contaminants and exposure to air. So once you take that screw out from here, you basically eliminate and destroy the hermetically sealed aspect of this from the factory, and then that's it. Once that's done, then the gas air gets in there, moisture gets in there, and the surface of the mirrors will be compromised, and the attenuation will be completely compromised, and then this out the door. So that's why they say that if you remove this, you permanently damage it. That's the reason, and that screw must be where they, you know, purge the gas out. They have to have somewhere for the gas to come out, and that's probably how they do it. It's pretty interesting to see, and you can see that there is sealant around where the initial fiber was connected to. So that's all consistent with this being completely sealed up. Pretty neat to see the amount of effort that's gone into making this. So let's do a very quick experiment here with this. I have connected a multimeter across the potentiometer of this decoder over here, and then I also have applying DC power to the motor. So I should be able to turn the motor here by turning the power supply on. Now before I do that, I've connected them to these two instruments there. At the bottom we have the Keithley 2280S, which is a high precision power supply, and at the top we have the Keithley DNM7510 7.5 digit multimeter. I've done an extensive review of this. If you haven't seen it, check it out. There's a lot of cool experiments in there. So let's go ahead and put this into ohm meter mode. And there it is. You can see it's reading 1.23 kilo ohm. And I can rotate the wheel manually by hand. And you can see the resistance changes. I can go up and down. But if I go ahead and turn the power supply on here, I should be able to turn the motor on. So let's go ahead and turn the power supply on and take a look at the motor. Now the power supply is set to 1.2 volts. If I turn it on, you can see, there it is. It's spinning. It's spinning pretty quickly. It's consuming about 55 milliamp. So it's spinning a little too fast. Let's go ahead and change the voltage, maybe bring it down. Let's go to, I don't know, 0.9 volts. Yeah, 0.9 volts is fairly reasonable. You can see that it's rotating just a little faster than 1 RPM there. I'm sorry, one rotations per second. So now let's go up here. There it is, and you can see very clearly the resistance continues changing. But because this is a very fast instrument, I should be able to get a reasonably good plot. Where are you, plot? There it is, look at that. You can clearly see very nicely the ramp there. So let's go over there. Let's clear the data, because we don't want to look at all of it at once. And go back, and there it is, check it out. And you can see quite repeatable, and so obviously this is sometimes missing some samples because it's not sampling fast enough, but you can clearly see the ramp, and it's changing between somewhere close to 0 ohms to 5 kilo ohm, which is the rating of the potentiometer. So there it is, and this is indeed how they close the loop. They use the value there, and they compare that with some reference analog voltage that's created by that DAC that you saw, and they grab that value from the calibration memory, and then fix the location of the wheel, which is pretty nice. And if I stop the wheel by my hand, you can see that it stops changing, and let it go and goes back to triangular shape again. Very nice. And this DC motors are quite good. I mean, running sub 1 volt fairly consistently. There's a little bit of you can see the current changes a little bit, so there's a bit of a catch. It's not perfectly smooth, but that doesn't matter anyway because it's in a feedback and network anyway, so it takes care of that automatically. And I should be able to, with this one, graph this thing. Graph view. Yes, I do want to view. There it is. So you can see that the current is not perfectly stable. And if I stop the wheel by my hand, you can see the current shoots way up because I'm stalling the DC motor. I'm going to let it go. The current comes back down. It's a really nice power supply. Very high precision, 6.5 digit power supply. Very nice. Anyway, so having said that, I hope you enjoyed this quick video. I think these signal path short episodes are more relaxing, just watching casually, nothing exciting, not very long. And these are not charged to the Patreon account, so these will not be, my supporters will not have to pay for the short episodes. I don't think that's quite fair, even though I think they're still pretty interesting videos. But anyway, I want to keep the Patreon only for the full-length videos and extensive videos. Anyway, if you like it, give it a thumbs up, and I'll see you next time.